Chapter 5 is all about thermochemistry. So we're looking at how heat changes during chemical reactions. The complete combustion of ethanol to form water and CO2 at constant pressure releases 1,235 kilojoules of energy per mole of ethanol burned. Write the balanced thermochemical equation for this reaction. Draw an enthalpy diagram for this. An enthalpy diagram. All right, so this is the thermochemical equation. Thermochemical equation is a chemical equation, and along with that, you show what heat is absorbed or released during the reaction by having a delta H. The little naught stands for standard conditions. So this reaction releases 1,235 kilojoules. All right, so they want this written in as a enthalpy diagram. Well, I guess what they want with an enthalpy diagram is they want to show how potential energy relates to heat energy. So with an exothermic reaction, right, that's what the negative sign implies on delta H, that I'm releasing heat energy. Lowering potential energy of the system, right, going from reactants to products. And the difference between the potential energy of the reactants and the products is a measure of how much heat is being released by this reaction. So, if you law of conservation of energy, if you lose potential energy, it's released as heat energy. Energy isn't created or destroyed, it's just converted from one form to another. Number 43, consider the following reaction. All right, so we get a thermochemical equation for the combustion of magnesium. Is this reaction exothermic or endothermic? Well, the negative sign on the delta H indicates that it's an exothermic reaction, right? Energy is being released. Endothermic reaction is when you have to put energy in to make it happen. Calculate the amount of heat transferred when I have 3.55 grams of magnesium reacting under at constant pressure. All right, so with thermochemical equations, we get a new conversion factor, right? So they want to calculate the amount of heat transferred. All right, so if they give us grams of magnesium, right, the molar mass of magnesium can be used to convert to moles. And now the new conversion factor. According to the balanced equation, for every 2 moles of magnesium used, you're releasing 1,204 kilojoules. So that's my conversion factor, right? For every 2 moles being burned up, that's the amount of heat released. So I can multiply across, grams cancel, moles of magnesium cancel, and I'm left with kilojoules being released, right? I didn't have a mole, so I'm going to release less than a mole's worth of heat. I should say I didn't have 2 moles. 2 moles would have released 1,204 kilojoules. 3.5 grams isn't 2 moles. All right, C. How many grams of magnesium oxide are produced when you release only 234 kilojoules? All right, so we'll go on in reverse, right? We have the amount of heat release, so how many grams does that represent? So again, we go to the thermochemical equation for the conversion factor. For every 2 moles of magnesium oxide made, you're releasing 1,204 kilojoules. So this gives me a way to convert from kilojoules to moles of the product in this case, and I can use the molar mass of magnesium oxide to convert to grams. All right, problem D. How many kilojoules of heat are absorbed when 40 grams of magnesium oxide solid decompose into magnesium solid and oxygen gas at a constant pressure? All right, so what they're saying is we're doing the reverse reaction, right? So instead of magnesium reacting with oxygen to form magnesium oxide, we're pulling magnesium oxide apart to form magnesium and oxygen. So if it's energy releasing in the one direction, right? Exothermic, when you burn magnesium, we know that, right? A lot of big bright light. That means that if I want to go the reverse direction, it's an absorbing process and absorbing to the same magnitude. So if you're releasing 1,204 kilojoules when you burn it, if you want to decompose it, you got to put that amount of heat in. So now when I answered this, right, I got 40.3 grams of magnesium oxide. Molar mass of magnesium oxide converts to moles. For every 2 moles of magnesium oxide being decomposed, you're absorbing 1,204 kilojoules. So an important point with thermochemical equations. If you reverse the direction of the reaction, you change the sign on delta H. All right, with number 47, we're dealing with a thermochemical equation for the combustion of methanol. All right, A, what is the enthalpy change for the reverse reaction? All right, so I'm burning methanol and releasing 726.5 kilojoules in this direction. If I turn the reaction around, all right, so it's exothermic in this direction. If I turn the reaction around, it's now endothermic to the same magnitude. So exothermic in one direction, all right, so the combustion of methanol, if I'm going to take carbon dioxide and water and react it to form methanol, I'd have to absorb 726.5 kilojoules. All right, B, balance the forward reaction with a whole number coefficient. All right, so they don't, instead of 1 mole of methanol reacting with 3/2 of a mole of oxygen, they want whole numbers. So to get rid of that denominator, that 2 in the denominator, I've got to multiply the thermochemical equation by 2 to get rid of that divided by 2 in the bottom in the denominator there. So whatever I do to the equation, I've got to do to the delta H. So if I multiply the equation by 2, I've got to multiply the delta H by 2. So instead of 1 mole of methanol reacting with 3/2 of a mole of oxygen, I got 2 moles of methane reacting. So I'm going to release twice the heat. So whatever you do to the thermochemical equation, you do to the delta H. C, which is more likely to be thermochemically favored, the forward rate of reaction or the reverse rate of reaction? All right, so in this situation, exothermic reactions are going to a more stable state. You're lowering potential energy because you're releasing heat energy. So that's how we look at it. A lowering of potential energy is going to a more stable state. So I'm going from a higher potential energy to a lower potential energy, and the difference between the potential energies is the amount of heat released. All right, for part D, if a reaction were written to produce gaseous water instead of liquid water, would you expect the magnitude of delta H to increase, decrease, or remain the same? I'm assuming what they mean by increase is become more positive, more endothermic. Decrease, become more exothermic. Stay the same. Explain. All right. In order for liquid water, as we know, to go to gaseous water, you have to put heat in. Actually, if you're going to go from 2 moles of liquid water to 2 moles of gaseous water, I looked up on the internet, and it's going to cost you 81.3 kilojoules. I'll have to put in 81.3 kilojoules. All right, so using Hess's law, if I added these two thermochemical equations together, liquid water goes into the reaction the same way it comes out, so it cancels. And when I add these together, I get gaseous water being produced. So whatever I do to the equations, I do to the delta H. So when I add positive 81 to negative 726, it becomes less exothermic, right? So the delta H increases. So that was a very long way of saying it becomes more endothermic. Or less exothermic, more endothermic. Okay. Specific heat of octane is 2.2 joules per gram per Kelvin. All right. How many joules of heat are needed to raise the temperature of 80 grams of octane from 10 degrees Celsius to 25 degrees Celsius? All right, so this is a different problem. We're utilizing the equation Q is equal to NC delta T, which means that, which takes in consideration, should say, how much material you have, how hard it is to heat up, and what the temperature change is. So when I plug into this thing, I've got 80 grams of octane, and you'd have to put in 2.2 joules per gram per degree Celsius to raise the temperature 1 degree. Well, you're not raising it 1 degree, you're going from 25 degrees Celsius to 10 degrees Celsius. So really, Q is equal to NC delta T is just a conversion factor to get to joules. When I multiply across, grams cancel, degrees Celsius cancel, and I'm left with joules. So everything just has to be in the right unit. Grams, degrees Celsius will cancel, and you'll be left with joules. So many joules is required. All right, B, which will require more heat increasing the temperature? 1 mole of octane. Which will require more heat increasing the temperature of 1 mole of octane by a certain amount, or increasing the temperature of 1 mole of water by the same amount? All right, so really what they're looking at here is which one's harder to heat up, octane or water. So when I didn't finish yet. They wanted, I'm sorry. With A, we want to convert to kilojoules. All right, so now we've got a special answer, right? So a lot of joules, let's get into kilojoules, easier to look at. So when we look at B, it's a question of how hard this is to heat up. So if I'm talking about a mole's worth, for every 1 mole of octane, it weighs 114 grams. I want to use this as a conversion factor to go to joules per gram per degree Celsius per mole. So when I multiply across, grams will cancel, and this is how hard it is to heat up a mole of octane. When I do the same thing for water, it's less. So it requires more heat to heat up a mole of octane than it does water.